In this video, we'll be talking about our first continuous distribution. It's going to be the continuous uniform distribution. So it's similar to the discrete uniform distribution we covered in the previous video, but it's, well, continuous, and we'll see what that means right now. So we say that the random variable x is distributed as uniform from a to b, and this a to b is an interval on the real line. So if we have the real line here, a is here and b is here. Okay, so we have conditions, obviously b must be greater than a, or else it's a non-interval. Okay. And also, I tend to write the closed brackets here. It doesn't matter if you write closed brackets or open brackets. I've seen a lot of textbook write the open brackets instead. Open brackets, I mean parentheses. So they'll write a comma b like this instead. It doesn't matter with continuous because the probability of a single point event, whether we choose to include a and b or not include a and b, doesn't matter. The probability of those events are zero. It doesn't really take away or add anything. Okay. Now that if you do that in discrete case, it is different because if you include a or b, it's different if you don't include A or B because these are discrete events. Okay, so keep that in mind. So now, what's the definition of this guy? So in the previous video, we had that a car was driving down the road, right? And it could either stop at house 1, house 2, house 3. It can only stop at certain houses. It can't stop like in the middle of houses. So that's discrete because it can only stop at certain points. But now we're going to remove that restriction. So I'll draw a little picture here. So if we have this car, let's say it starts at A and it can only go until B. It can't go past B. It can stop at any point on this interval right here. And furthermore, the point that it stops at is equally likely with all other points. So let's say if we ask ourselves, what's the probability that it stops at A plus B over 2? Well, the answer to that question is actually 0 because a single point event is 0. But the real question we should ask is, what's the probability that it stops in this interval from A to A plus B over 2 compared to the probability that it stops in this interval, A plus B over 2 to B? Since they're the same length, we're going to say the equal probability. So that's how you define the uniform distribution. In this interval it's defined on, if you pick two subintervals of the same length, the probability of landing there is the same. Okay, cool. So now let's give a formal definition of let's give the PDF of this random variable. So before we were dealing with PMF, probability mass function. Okay, so now we're going to kind of use physics analogies here because that's the best way to understand it, I believe. We were dealing with probability mass functions. Here we don't have mass at particular points because there's 0 probability events. We need to talk about densities and convert that to mass, and I'll show how to do that. So let's write the PDF probability density function. So the PDF of this uniform is given by f. This is typically how I write it. You put the random variable in question, big X, and then you put the stand-in variable for it. So I put little x here. I'll distinguish them by writing this as curly for now. Okay, so this is equal to 1 over b minus a and 0 otherwise. We still need this otherwise. And this is defined if this little x is less than or equal to b, greater than or equal to a. Okay, let me describe what this means. So this is saying the density at any given point on the real line. So I can ask about the density at any point on the real line, right? Let's say I ask about the density at a plus b over 2. Well, that is between a and b, so therefore we're in this case. Therefore, the density there is 1 over b minus a. Notice this density here is constant. That's not something that's going to be true in general, but since this is uniform, the density is constant. And what does that mean? That means that no matter where I pick my point in this interval, remember in this interval, the density is going to be constant. And since density is mass times volume, okay, so volume, I'm going physics analogies here. You shouldn't read too much into this, but how I thought of probability when I first learned was I had this density and I wanted to multiply by the volume, and I took volume as a length of a small piece of interval, so like dx. If I multiply dx by this, I will get the mass because volume times density gives you mass, correct? So that kind of tells me that if I go anywhere on this interval right here from a to b, and I multiply 1 over b minus a times the volume there, which is dx, I will get the mass. And since that's constant, dx is the constant, and 1 over b minus a is constant, that tells me the probability at any point in this interval is the same, which is consistent with what we described the uniform random variable, the continuous, to be. It's same probability in all parts of this interval. Furthermore, it's 0 outside, because let's say I pick something over here, like b plus 1, or maybe a minus 1. What's the density that is going to be here? So the density must be 0, because the way we define this car is that it can't go anywhere behind a, it can't go anywhere past b. Therefore, the probability mass, or the probability over there, must be 0. Therefore, the density must be 0. Okay? This is how we define this guy. We'll do a graph of it, probably at the end. Okay? So the next thing we want to talk about is making sure this is the correct probability density function. And how we do that is we need to make sure it integrates to 1. So in the previous videos when we were talking about discrete random variables, discrete distributions, we had that we had sums, right? Now we need to have integrals because we're dealing with continuous points. We can't have sums anymore. So let me write the check and then I'll explain what's going on. So minus infinity to infinity, f x x, we're going to put dx, okay? So what does this mean? So here I've written the probability density. So in fact, let me even label it. This is going to be the density. And like I said before, this dx is kind of like the volume. In reality here, it's the length, okay? But you can think of it as volume. So density times volume gives you mass. So over here, and don't use these terms in your class. This is just kind of like how I think about it. So this is the mass. And if we integrate all the mass over the whole real line, we better get 1 because that's how probabilities are defined. They have to be 1 on their sample space. They have to add up to 1. Okay? So if we do that, we better get 1. Now this is the general form. This can be used, this general form for any continuous random variable. Let's apply it to this one. So this is actually what? So this fx of x is 1 minus b or 0. So all the times it's 0, this integral takes no value. So why are we even thinking about that? So really, this is equal to from a to b, 1 over b minus a dx. Okay, so all I've done is that I've noticed that every time this function is 0, this integral just takes 0 value. So why even bother to put that in our integral? So let's only consider the bounds where it actually takes a value and replace the function by the value, the density that it takes in that bounds. Okay, that's what I've done here. Now this integral is super simple. It's 1 over b minus a times b minus a. Cancel, cancel. We get 1. Just what we wanted. Okay, so that sanity check was a good idea because it let us check that this is the correct probability density function. Now let's just go on and do what we did for the other random variables. We're going to find the mean and the variance. So actually I like the continuous ones better because integrals are sometimes easier to work with because it turns out people learn a lot more techniques for integration and summation and when they're learning school. So these can actually be a lot easier and nicer even though they seem scarier. So this is actually a very nice one. So we want to find the expected value, right? So just in the summation case, what we do is take the integral from minus infinity till infinity. We want to do it over all possible values, first of all. We'll reduce the values we can take later. We multiply it by the probability density, fx, x. We want to multiply it by, since it's expected value of x, we want to multiply it by x here, and then put the dx, which is the volume, or the length. Okay, so now we're going to do the same thing. Since this function takes value 0 on so much of the real line, we're only going to restrict it to the parts where it does not take 0. Like that, and then we're going to put x dx. Now this is a nice simple integral compared to all the hard summation stuff we did in previous videos. So this is just going to be 1/2 x squared taken from a till b. So it's going to be 1/2 1 over b minus a. It's going to be b squared minus a squared, which is b minus a, b plus a. So this will cancel with this, and we're going to get a plus b divided by 2. That's the expected value. And really, you didn't really have to even do this calculation. I mean, you did if you want to prove it formally, but that makes sense, right? If it's equally likely on this whole interval, then it should make sense that the expected place to be would be the middle. And we see that that's true. Good. Let's find the variance. The variance is not so obvious, but we could do it. So the variance, remember, variance of a random variable is equal to expected value of random variable x squared minus expected value of the random variable x squared. Okay, this we just found. So this is going to be a plus b squared over 4 because I'm just taking this and squaring it. Okay, and then this will require work. So this is going to be again an integral. And I could start at negative infinity, but I think you get the idea. So I'll just start at ab. Okay, put the density. And I'll put x squared instead. Dx. This is also a nice integral to work with. 1 over b minus a. So it's going to be 1/3 x cubed. Taken from a to b, so we get 1/3 1 over b minus a. B cubed minus a cubed. So now we just need to remember the algebra property. We can do polynomial division here too. Not a big deal. 1 over b minus a. This is b minus a. It factors nicely. And the other factor is b squared plus ab plus a squared. Cancel, cancel. So what we get is 1/3 b squared plus ab plus a squared. Cool. and that's that. That's this. Now we need to subtract this. At this point, this is just algebra. Just make sure you don't make a mistake. Okay, so I want a common denominator of 12. So I'm going to multiply this guy by 4 and 4 on the bottom. So I'm going to get 4b squared plus 4ab plus 4a squared minus, and I want to multiply this guy by 3 on the top and bottom. So I'm going to get minus 3a squared minus 3ab. Sorry, it's going to be a 6. I'm making mistakes myself. And then you're going to have minus 3b squared. Divide all that by the common denominator we got, and let's figure out how this cancellation is working. So we have 4b squared minus 3b squared gives us 1b squared. We have 4a squared. We have minus 3a squared. Again, gives us 1a squared. We have 4ab minus 6ab minus 2ab. So we have a squared minus 2ab plus b squared. That's just a minus b squared over 12. That is the variance of a continuous uniform distribution. Okay, so you just take you find the difference between the bounds and you square it, and then you divide by 12. Okay, so this can be a little bit hard to memorize because the number 12 doesn't seem very related to this at all. This seems a lot more intuitive, but if you know, it's not terribly hard to derive if it comes to that. Okay, the last thing we need to do is find the moment generating function. It turns out not to be that hard. It's going to be expected value of e to the sx. Okay, so we're going to go through it again. So it's integral from a to b, e to the s little x, and then got to put the density, got to put the volume. Kind of want to stress that you shouldn't use this term volume. It's not really a proper term, but it's how I think about it, because in physics terms, this is the density times the volume, so that gives you the mass. And since that's just the probability, that goes back to the discrete case. It kind of helps you make that connection. If that helps you out, go ahead. If it doesn't, you can ignore me altogether. So this is 1 over b minus a, integral from a to b, e to the sx dx. Nice integral, 1 over s b minus a. So just taking this integral, taking 1 over s, e to the sx evaluated from a to b. So we get e to the sb minus e to the sa over sb minus a. That is our MGF. Let me put that. MGF of the continuous uniform distribution. We see that these are not nicer formulas. They don't involve the offset things we had in the discrete case, mostly because the bounds, it doesn't matter if you include them or not, those a and b. Okay, cool. So we have the MGF, and I guess the last order of business is to draw our graph of this guy, and it's a very boring, maybe you'll say, but pretty basic graph. So this is not a graph of value versus PMF. It's a graph of value versus PDF. Okay, so we have x over here, and we have f big X little x. You don't have to put the big X here. This is just something to remind myself that this is a PDF of this random variable. You don't have to put it. You can just put f of x if you would like. And I guess this can get confusing because you don't know which is cap, which is lowercase. But this is how I'll do it. Okay, and maybe in the future I'll try to name this different, maybe k. Okay, so what we have is that if we go to our formula again, remember it was 1 over b minus a from a to b and 0 otherwise. So if we have a here and we have b here, it's a constant value on this entire line. So if I just pick this as 1 over b minus a, then starting here, ending here, it's just a constant line, just like that. And we see that it's 0 everywhere else. So it's 0 forever in both directions. And that's it. And what we did with the integration in the beginning, when we tried to verify that it was equal to 1, all we did was we were finding the area under this curve. And we see we didn't have to do the integration because this is just a rectangle. The area of a rectangle is base times height. The base was b minus a. The height was 1 over b minus a. Obviously, had to be 1 right here. Okay, that's the uniform distribution. It's kind of the most simple, most boring case of the continuous distribution. So it's kind of like the Bernoulli of the continuous. But we see that it has a lot of applications, and we'll see how it relates to other distributions in the future.